Hi students, welcome to this lesson 2 on the mole. And as we carry on in this unit, we're starting to use this new unit, the mole, and we have to first understand what it is and then how to use it in our calculations. You might remember in the last lesson that we learned how to convert from the number of molecules to the number of atoms, or how to count how many atoms are in a molecule. And that's going to be really important because we're going to use that now in our calculations that we do in this lesson. But first we have to understand this idea of what is a mole, because this is a new unit for us. And it might help to think about what a mole is not. And for those of you that like the little animal, the mole, he's a pretty cute little guy. We are not talking about that mole. And if you think of a mole on your face or on your body, we're also not talking about that type of mole. So the type of mole we're talking about is a specific unit that we use in chemistry to represent a certain number. And let's talk about where it comes from. So we know that atoms are incredibly small, and we deal with atoms and deal with molecules in chemistry all the time. Because they're so small, counting atoms or counting molecules is not very convenient for us because we're talking in such huge numbers. For example, if you think about 12 grams of carbon, which is not that much carbon, 12 grams of carbon contains this number of carbon atoms. That's a humongous number. So you can imagine as we start to deal with bigger and bigger masses of carbon, we start getting astronomically huge numbers of carbon atoms. And that's not a very convenient unit then to working in atoms here. So the need for a unit that represents a larger number came early on in chemistry, and hence the mole. So the mole is actually also referred to as Avogadro's number, and we're going to look at its technical definition and then how to use this number also in calculations. So in the same way that if you think about a dozen, you're all familiar with the term a dozen. If I tell you that I have a dozen cookies, you know that I'm talking about the number 12. I have 12 cookies. If I tell you I have a dozen pairs of shoes, you know I'm talking about 12, and I have 12 shoes. So in the same way that a dozen refers to a very set standard number, which is 12, a mole is the same. 1 mole is equal to a very specific number, and it's this humongous number right here, 6.02 times 10 to the 23 of whatever it is that I'm referring to. So this can have any units depending on what I have a mole of. So a mole is often thought of like the chemist's dozen, except instead of 12, it represents a much, much bigger number. And so we had this need in chemistry, or scientists had a need to represent a large number of atoms or molecules with a smaller unit. And perhaps somewhat arbitrarily, carbon was chosen to be the substance or the element to experimentally measure and come up with a standard accepted number. And so this is where the number 6.02 times 10 to the 23 comes from. In exactly 12 grams of carbon, there are that many carbon atoms. And so Avogadro, who is the scientist who experimentally determined this number, the number is often named after him as well. So we call this Avogadro's number. And it's the accepted standard for the mole. So this is a number that we want to commit to memory as we carry on in this course. You'll be given this number on your assignments and on your quizzes to help remind you, but you do want to know this number. This is one of the things in chemistry, one of the conversion factors that we want to know really, really well. It is an experimentally determined number. It's actually a larger number than this, 6.022, and it carries on. But for convenience and simplicity, in Chem 11, we round it right here to 3 sig figs. So as we do our calculations, I'll come back to that. But it is good for you to know that it is actually, the number, it can be reported more precisely, but for our purposes, we round it at 6.02. Okay, and even though it comes from the number of carbon atoms in 12 grams of carbon, we can use this number, a mole, now to talk about any type of element whatsoever, because now we know that 1 mole is equal to 6.02 times 10 to the 23 of whatever we're talking about. Okay? I'm not going to talk too much about molar mass, but I've made a little note here because I just want to make sure that I am clear about the difference here between molar mass and a mole. So the molar mass is the atomic mass or the molar mass of an element. And if you look on your periodic table, for example, if you look at carbon, you'll see underneath carbon that there is a molar mass of 12.0. And those units are grams per mole, okay, or sometimes called atomic mass units. And so the 12 grams per mole here refers to the fact that 1 mole of carbon has a mass of 12 grams. Okay, you could also equally say, it would be equally correct to say that 12 grams of carbon contains 6.02 times 10 to the 23 atoms of carbon, because that's what a mole is equal to, except that's a lot of information on the periodic table, and we report the mass per mole instead. So molar mass refers to exactly that, the mass of a mole of that element. So later on we will have to use molar mass, and we will be able to convert between moles to mass to grams, or from grams all the way to atoms. We can do lots of different conversions, but that will come in a following lesson. So I will come back to molar mass a little bit later. So this number then, 6.02 times 10 to the 23, that is the standard for the mole. So a mole of anything then has this value. So for example, if I said that I have a mole of shoes, which by the way would be absolutely a crazy amount of shoes to own. If I did have a mole of shoes, I would have 6.02 times 10 to the 23 shoes, which I would never even be able to wear in my lifetime, but that's okay. You can have a mole of anything. If you had a mole of jelly beans, which again would be an absurd number of jelly beans to actually have, it would cover a large part of the earth. 6.02 times 10 to the 23 jelly beans is how many you would have. So you can see here that Avogadro's number itself doesn't have any units because you can have a mole of anything. But obviously in chemistry we don't talk about shoes and jelly beans very often. So that means that if you have a mole of magnesium, then you have 6.02 times 10 to the 23 magnesium atoms. What if you had a mole of manganese instead? Would it be the same? Of course, it would. 6.02 times 10 to the 23 manganese atoms. Okay, we're not concerned about mass right now because we're not being asked what's the mass of manganese or the mass of manganese or magnesium. We're just saying if you have a mole of it, then that's how many atoms you have. Because quite simply put, if you have a mole of anything, you have 6.02 times 10 to the 23 of that thing. Okay, this is really important and key for this lesson, to make sure that you understand that. So a mole of anything is equal to this, okay, to Avogadro's number. So from that statement then, we can come up with two conversion factors. 1 mole equals 6.02 times 10 to the 23 can be written like this. Okay, in a calculation with the 1 mole on the top of the conversion factor in the numerator, or it can also be written like this with the 1 mole on the bottom. And we would use one or the other of these conversion factors depending on what kind of units we're trying to cancel out of. And I will do those in the calculations that follow. It is important to know here that there are no units associated with Avogadro's number because it's a number. Just like a dozen is a number, a dozen doesn't refer to any particular type of item, but we can put units on it. So if we're talking about a mole of an element, okay, then we can talk about atoms of that element. If we're talking about a compound, we can talk about the moles of a compound. We can talk about that number of molecules of that compound. Okay, so but on its own, Avogadro's number doesn't have any units associated with it. So you can think of it just like the chemist doesn't, but a much bigger number. This brings me to the mole conversion chart that you are given in this course. You're given this mole conversion chart to help you on assignments and quizzes and in your questions that you do in the textbook. You aren't able to use this flow chart on your tests because by the time you get to it, there will only be actually two numbers that you need to know. One will be the mole, and the other will be this volume up here that we will talk about in an upcoming lesson. So we won't worry about that right now. All right, but it is helpful while you're first learning to be able to have a chart that you can go to remind you of what you need to do when you're converting. So if you look at this chart for a minute, this is called the mole conversion chart. You'll notice that the mole is right in the center of the chart. It's like the heart of all of our calculations in chemistry. The majority of calculations that we need to do require us to go through the mole. So for example, if we're talking about the mass of an element like 12 grams of carbon, and if we're asked how many atoms of carbon are in 12 grams, it's not possible for us to go directly from grams to atoms without crossing through the mole. Okay, so this chart is going to be helpful to us in the beginning as we're doing our calculations, and it's important for us to understand how it works. So in the center is the mole. Up here on the left hand side you can see that we have mass. Okay, so that's when we're being asked to calculate mass, for example, or we're starting with mass. And to get from mass to moles, we use the molar mass off of our periodic table. We'll talk more about that in another lesson where we're actually doing some of these calculations. Another unit that we are sometimes asked to convert to is liters. So for example, if we're talking about the volume of a gas at standard temperature and pressure, there is a specific conversion factor that we can use to convert from liters of that gas to moles and vice versa. We're not going to talk about either one of these two boxes right now because we're not going to need to use them yet. What we are going to use is down at the bottom here. We're going to have to know how to go from moles to the number of molecules in for example, in a compound, or how many molecules there are in a certain number of moles. And this is where we use Avogadro's number. The other time we can go straight from moles to atoms is when we're talking about single atoms. So I'll give you an example of what that is. So if a single atom would be like a atom of iron. So if we're told we have 1.2 moles of iron and we're asked how many atoms of iron, say solid iron, we can go directly to the number of atoms of iron. Okay? Another good example would be like helium, for example. If we were talking about atoms of helium gas, we can go directly from moles to atoms because helium is not part of a compound. It's just a single atom. It's a noble gas and it doesn't react with anything. So when the substance that you're looking at is a single atom, then you can go directly from moles to atoms. Any other time, if you're asked to find the number of atoms in a substance, if it's part of a bigger molecule, then there's one more step that we have to do here. Okay, so for example, if we were asked to find the number of chlorine atoms in CCl4, then we would be able to go from moles of the substance to the number of molecules of CCl4, but that only tells us how many molecules of CCl4 we have. In order to figure out chlorine specifically, how many atoms of chlorine we have, sorry, that should say CCl4, my apologies, the Cl is here, to figure out how many atoms of chlorine we have in CCl4, we would have to do one more step, which would be to count how many chlorine atoms there are in CCl4, and there's 4. So we'd then have to use that second conversion factor, that there's 4 atoms in one molecule, okay, to do the last step. So that would be a 2-step calculation if we're going from moles to atoms of chlorine here. I'm going to do some of these calculations with you, so this makes some sense, but it is important to just distinguish on this chart very clearly. If you have to go to atoms, you will almost always have 2 steps, okay, from moles to atoms, unless you're talking about a single atom, like a single solid iron, okay, or helium. So when you're talking about something in elemental form, you can go straight to it, okay, because there's no need to count. There's only one type of atom in that substance. Okay, let's go ahead and do our calculations together. Let's try some out. So here's our first question. How many moles of sodium bromide are there in 1.7 times 10 to the 25 molecules of sodium bromide? So our first step here is to think about where we're going and to make our plan. I will come back to this way of setting up our calculations using dimensional analysis, which is just a fancy term here to say what I want equals what I have times what I know. Remember that what you know is your conversion factor, okay? And we're going to follow this setup when we do our calculations. So what do we want here? We want how many moles. So we're looking for moles. We would like to know the number of moles are in 1.7 times 10 to the 25 molecules of NABR. So what we have is this number of molecules. Okay, and what we know is going to be the conversion factor then that takes us from molecules. And let's be careful here when we're looking at what it is it's asking. It's asking how many molecules of NABR. It's not asking us how many atoms of sodium or atoms of bromine. Okay, so we're going from molecules to moles here. So if we look back at our chart for a moment, we're going between moles and molecules. So here we are in molecules and we're converting this time to moles. So we're going to use Avogadro's number as our conversion factor. 1 mole equals 6.02 times 10 to the 23 molecules. So let's write that out. This is going to be our conversion factor. So this is what we know. Okay, 1 mole equals 6.02 times 10 to the 23 molecules of NABR. Great. So I'm ready to put that into my calculation as my conversion factor. I'm going to put the 6.02 times 10 to the 23 molecules on the bottom because I want it to be directly across from the units that I'm trying to cancel. I'm trying to cancel out of molecules, so I need to make sure my molecules are on the bottom so that they're going to cancel. So I've got 6.02 times 23 molecules, and I will write molic for short. Okay, and make that look like a 3. And on the top of my conversion factor, I'm going to put the 1 mole. There's the other half of my conversion factor. Right away, I'm going to cancel out my units. Molecules are canceled. Molecule divided by molecule is 1. So now I'm ready to go ahead and calculate. I'm going to multiply 1.7 times 10 to the 25 by 1. I don't really need to do that. It's not going to change my answer. So I'm essentially going to just divide by 6.02 times 10 to the 23. And my answer here is going to come out to be 28. If I leave some decimal places, 28.239. And my units are moles now. And before I say I'm finished, I need to look at my significant figures. And in this question, my original data had 2 sig figs in it. 1.7 has 2 sig figs. Avogadro's number does have 3 sig figs, but we're limited in a multiplication division question to the least number of sig figs. So we can only have 2 sig figs in our answer. because of the 1.7. Okay, so I'm going to go ahead and round this number then to 28. So this is my answer. It's equal to 28 moles. Or I could also write that as 2.8 times 10 to the exponent 1 would also be totally acceptable and would have the correct number of sig figs. And that's my answer. Let's try another question. Here we have how many molecules of lithium chloride are in 0.5 moles of lithium chloride. Okay, again, let's determine what it is we're looking for. What do we want? We want the number of molecules. There's what I want. What do I have? I'm starting with moles of lithium chloride. So I can start by setting up my calculation right away. I'm looking for the number of molecules. That's what I want. It's equal to what I have, which is 0.5 moles. Always keeping my units in my calculations, times what I know. Now, what do I know here? What is my conversion factor? Let's think about our plan. Well, here we're converting from moles to molecules. And I'm still talking about the same type of substance. So I'm talking going from moles of lithium chloride to molecules of lithium chloride. So I can go back to my chart here, and I see this time I'm just going the opposite direction. So I'm starting with moles, and this time I'm going to molecules. And so again, I'm going to use my Avogadro's number, 1 mole equals 6.02 times 10 to the 23 molecules. So there's my conversion factor. I just need to think about how I'm going to put it into my calculation. This time I'm trying to cancel out of moles, so I need to have that 1 mole on the bottom. And the 6.02 times 10 to the 23 can go on the top here. And I'll keep my units in here. That's molecules on the top. And right away I can cancel out of moles. And then I can go ahead and calculate out my answer. 0.5 times 6.02 comes out to 3.01. Okay, times 10 to the 23. And my units are molecules. And before I finish this up and say I'm done, I need to check my sig figs. So I come back to my question for a moment, and I can see that in my original data here, I actually only have 1 sig fig. So 0.5 has only 1 significant figure. So I'm only allowed to have 1 sig fig in my answer then, because this was a multiplication division question. So I need to round right there, okay? And so my answer is going to come out to be just 3 times 10 to the exponent 23 molecules. And that's my final answer. Let's try a couple of questions that are getting a little bit trickier then. Okay, here's a question. How many atoms of chlorine are in 6.2 moles of carbon tetrachloride? Okay, CCl4. So this is one of the questions that I was referring to, where we have to be a little bit careful here, because it's not asking us how many molecules there are in 6.2 moles of CCl4. It's actually specifically asking us about how many atoms of chlorine there are in this compound. So that's fine. Okay, we can start by realizing that this is what we want, and the 6.2 moles is what we have to start with. So let's start our calculation off that way. So we're looking for the number of atoms of chlorine specifically. And we have 6.2 moles, okay, of CCl4. And we're going to multiply that by what we know. And here we might have to have more than one conversion factor. So if we think about this for a minute, we are able to convert from moles to molecules of CCl4 but there will be an extra step in order to get to the number of atoms of chlorine. So if we look at a chart here, our first step is going to be to go from moles to molecules. So that will be step number 1, and we'll use the conversion factor of Avogadro's number. And then in the second step, because we're looking specifically for the number of chlorine atoms, we're going to have to count the number of chlorine atoms in a molecule of CCl4, and that will be our second conversion factor. So we're going to have, in our plan here, we're going to have 2 conversion factors. So the first one is going to be that there is, in 1 mole, okay, there is 6.02 times 10 to the 23 molecules. And the second conversion factor we need then is that in 1 molecule of CCl4, there are 4 chlorine atoms. So this is one of those questions where we just have to count then the number of atoms, which is something that you did in the last lesson. You learned how to count the total number of atoms. There's 5 atoms altogether in this compound, but specifically looking at chlorine, there's only 4. Okay, so let's go ahead and apply that now and put these conversion factors into our calculation. So the first one is going to be converting from moles to molecules. I want to cancel out of moles, so I'm going to put my 1 mole on the bottom, and the rest of my conversion factor goes on the top. Okay, and right away, let's cancel out of moles. Now I'm in molecules of CCl4. And my second conversion factor is to put in my molecules and my chlorine atoms, and I need to put my 1 molecule on the bottom. Okay, so 1 molecule of CCl4 can go on the bottom here, and then the 4 chlorine atoms can go on the top. And right away I'm going to cancel out of molecules. So now I'm left in chlorine atoms, which is what I wanted, and I'm ready to calculate. So I can go ahead and put this into my calculator. I'm going to have everything on the top is being multiplied, and anything on the bottom is, I'm dividing by anything on the bottom, but I only have 1s on the bottom. So I'm going to multiply 6.2 times 6.02 times 10 to the 23 times 4. And my answer, with some decimal places, is going to come out to 1.493 times 10 to the 25. And I'm in atoms now of chlorine. Okay, and again, before I finish up, I want to look at sig figs. And if I come back to the data that I used to calculate, I had 2 sig figs in my number 6.2. I have 3 sig figs in Avogadro's number, so I'm limited by the 2 sig figs up here. And being very careful here, remember that we do not include counting numbers when we're thinking about the number of sig figs we're allowed in our answer. So we ignore counting numbers as well as exact conversions or perfect conversions when we are applying the rules for sig figs. So the number 4 here is not going to limit us to 1 sig fig. Okay, that's a counting number and it's ignored. So I'm allowed to have 2 sig figs then in my answer, which means that I need to round right here at the first decimal place. So that 9 will round up my my 4 to a 5. So my answer is 1.5 times 10 to the 25 atoms with 2 sig figs. And we're always putting units in our answer. Okay, otherwise our number is a bit meaningless without units. I'm going to do one final question. Thanks for sticking with me. It's a long video. And I did this question because there's one like it in the assignment. And it's also a question that sometimes throws people off because they get really used to working in units of atoms and molecules, and other types of units are sometimes confusing. So this question says, a reaction emits light at a rate of 9.41 times 10 to the 29 photons per second. Okay, how many moles of photons are emitted per minute? So it's okay if we're not working in atoms here or molecules. A photon of light is a perfectly acceptable unit as well. And remember, the Avogadro's number can be used for anything. So a mole of photons is equal to 6.02 times 10 to the 23 photons. It works just the same as it would for an atom or molecule. So our task ahead of us is just to figure out what the plan is and what are we needing to convert here. So this question is asking us for moles per minute. So that's what we want. So what we want is going to be moles, okay, per minute. And what we have is 9.41 times 10 to the 29 photons per second. So there's two conversions that we need to make here. The first conversion that we need to make, and really the order here actually does not matter because we're talking about a rate, so whether we want to convert our time units first or from photons to moles first, it actually doesn't matter. We just need to go ahead and choose one. Okay, so we'll say that the first thing we'll convert is our photons to moles. Okay, so the conversion factor we're going to need for that is that 1 mole of anything is equal to 6.02 times 10 to the 23. So 1 mole of photons then is equal to that many photons. So that's the first conversion factor. And then the second conversion factor is just converting from seconds to minutes. And we know that 1 minute is equal to 60 seconds. So we can go ahead and now plug those in and convert. Just move my calculation down a little bit. Alright, so let's go ahead and put in our first conversion factor, and this time I'm trying to cancel out of photons, so I want to make sure my photons are on the bottom. So 6.02 times 10 to the 23 goes down here, and my 1 mole needs to go on the top. My photons are going to cancel. Okay, and the next step is to convert from my seconds to minutes, and I have this time seconds is on the bottom of my my rate. It's in the denominator, so I need to make sure that I put the 60 seconds up here in the top so that they do indeed cancel. Okay, and my 1 minute is going to go on the bottom. And now the only thing I haven't canceled is moles per minute, which is what I want, so I know I'm ready to calculate. And I can go ahead and I multiply anything on the top and I'm going to divide by anything on the bottom. My answer is going to come out to be 9.3. If I leave some decimal places here, 9.3787 times 10 to the exponent 7. And my units are moles per minute now. And looking at our sig figs before we say we're finished, we had a total of 3 sig figs here. Okay, 3 sig figs in Avogadro's number. Remember that time is an exact conversion. There are exactly 60 seconds in 1 minute, so we are not limited by the 1 sig fig that we see here. Okay, so we can ignore exact conversions when we're looking at significant figures. So that means that we are allowed to have 3 sig figs in our answer, and so I'm going to have to round it right there, and that 8 is enough to round this 7 up to an 8, so I'm going to report my answer as 9.38 times 10 to the 7 moles per minute. And that's my final answer. That's the end of this video, and hopefully as you approach the assignment and the quiz, this will make sense to you, but definitely do the questions that are assigned in Hebden and make sure you check your answers in the back so that you are feeling confident about these types of calculations. Best of luck.